If you have ever been in that kind of situation before, then welcome to the fourth and final episode of this series called Calculus for Dumb Babies. In this series, I will try to teach you guys calculus in a way that is simple and intuitive. So whether you are just like a primary student who may have some interest in the subject, or maybe you are someone who may have graduated but haven't really touched calculus in a while and wants to revisit some of the ideas, this series will be perfect for you. In this episode, we'll explore the formal definition of what we call integration, continuing from the three previous episodes which explored the overview of the calculus, the definition of what we call limits, and the definition of what we call differentiation, which is another major part of calculus. So if you haven't checked that out, you can click the eye in the top left or right hand corner, or click the link in the description below. And don't forget to give me a like, subscribe, and comments if you enjoy my content. So with that said, let's begin, shall we? Okay, so before we proceed to the content of today's video, let us recap what we did in the three previous episodes. So in the first episode, we looked at two separate problems that actually leads to the two fundamental ideas in calculus. The first problem is the problem about the area of the circle. This was proposed by the Greeks, and it actually leads to the fundamental idea of what we call integration. And for the second problem is about the speed meter on how your car actually displays the speed when you drive, and that actually leads to the fundamental idea of what we call differentiation in calculus. And let me recap you a bit further into each of these problems. So for the problem of the area of the circle, the philosopher that worked on this problem actually came up with a very clever solution on how to find the area of it. So what he did is he sliced the circle into a sort of pizza slices, something like this, all right? So it can be like 8 slices, which should be something like this, into these slices. And then what he did is he rearranged these slices into a shape that resembles a bit kind of like a rectangle. So for 8 slices, it's going to be resemble something like this. For 16 slices, which means we cut even deeper into the circle, that will actually result in a shape that looks much closer to a rectangle. And similarly for 32 slices, we can chop this up further, and that will actually gives a shape that looks even more like a rectangle. And what he realized is if we continue to cut infinitely many slices, then this is going to result in a perfect rectangle and allows us to compute the area of the circle to be what we know as pi r squared, something like that. All right, so that is the first problem, and the idea of chopping into small pieces and then summing them up together, that is the idea of integration, and that will be the idea that we look at in today's video. Now, another problem that we also tackle in the first episode is the problem about the speed meter, in a way that when your car displays the speed, the definition of speed is the change in distance divided by the change in time, right? But your car actually displays the speed at every moment in time. Just look at it when you drive your car, right? There's a speed at every time, but the definitions say that it has to be change in distance divided by the change in time. And so there's a bit kind of contradiction here. And so we look into how your car actually overcome this contradiction. So what your car does is it actually move a tiny step in time, and that tiny step in time can be something like 0.01 or 0.001, something like that in time, like a very small interval, and it actually compute the speed, compute the change in distance over the change in time of that small interval, and that's how it arrives at the speed that looks like instantaneously. The way that we actually just kind of move a very small amount and then compute the change, that is the fundamental idea of differentiation in calculus. And so those two are the main ideas that we covered on the first episode. And in the second episode, what we did is we tried to look at how are we going to define these two operations. We realized that if we go for like the most straightforward way and just say that, okay, number of slices may equals to infinity, change in time may equals to 0 or something like that, we run into contradiction, because in mathematics we can't really have things equals infinity, because infinity isn't actually a number. Infinity is just a concept of getting larger and larger and larger without any bounds. And similarly for change in time, if change in time is equal to 0, then this is going to be something like 1 over 0, like because change in time is actually in the denominator part, right? And so it's going to be something like this, and this is mathematically undefined. And so we can't really go with the direct approach of actually defining these two operations. And so we invented a tool that allows us to quantify and allows us to write a compact notation for this kind of process we're actually working on. And that tool is what we call limits. So the idea of limit is that the slices isn't equal to infinity, but it's a value that is approaching infinity. And similar thing for the change in time. It's not zero, but it's something that is approaching zero. And so by writing this, it allows us to get that kind of sense without breaking the rules of mathematics. And we actually write it in this compact notation right here. So the notation may look a bit scary, but essentially this is say that for a tiny amount in time h is just a number, by the way. It can be something like 0.01 or 0.001 or something like that. For a tiny amount h step forward in time, as h approaches zero, then that is going to be the speed. And in the third episode, we actually work out the formal definition of speed that is in the dot right here. Similarly for the areas, for example, if you have the number of slices be n can be any number. For example, if you have 8 slices, n is going to be 8. If you have 16 slices, n is going to be 16. And if you have 32 slices, n is going to be 32, and so on. So what we are saying is that if the number of n approaches infinity, remember that it's not infinity, but it's approaching infinity, then that is going to be the area of the circle. And so this is the brief summary of first and second episode of this series. In this episode, we'll actually look into what exactly is in this thing right here. So in the case of the circle, it's actually like not general, because this idea of just chopping into small pieces and then summing them up together, I mean, it's a general idea, but we just apply it to the case of the circle. So now let's actually look into a more general case on how are we going to actually define this idea in terms of graph, which is a general form in mathematics. And by working out this general form of integration, we can then maybe apply it more into the problems we actually face. For example, the area of the circle. You might be curious on what this symbol actually is. So this symbol is actually what we call functions. And essentially this is just like y value. So I can just write it another way as y, but in this way it's much more convenient, because when we work with the other graph, then we can just assign maybe it's like g of x, h of x, or something like that. And it's more common than just kind of writing y1, y2, and so on. So when we're working with multiple graphs, we often use it this way. And also that when we work with this notation, if you want to evaluate the value at specific position, for example, at x equals 3, and remember, the x is just like the horizontal axis, right? I named this x, and this is the vertical axis, is called y. If we want to evaluate the function at x equals 3, which is this the point right here, we can just write f of 3, and that's simple notation just kind of signifies that we want the y value at that position. And so it's much more compact if you compare to just like writing an ordinary y symbol. Another thing is that it's called function because in this case we are actually inputting x and then it outputs y. With this stuff in mind, our task here is to determine the area under the graph. And what I mean by the area under the graph is this. You see, our graph is something like this, right? And the area under the graph is simply the area that is like the graph actually is enclosed thing that I'm shading right here. In doing so, we'll be utilizing the idea of integration, which you remember is by chopping into small pieces and then summing them back up together, all right? And so how do we do that? So let's say we are evaluating the area of the graph between this interval right here. So let's say it's between x equals 2 and between x equals 4. So basically we are evaluating the area around this part. In the case of the circle, what we did is we begin with 8 slices, and that isn't really that accurate. So increase to 16 slices, and then we increase to 32. And we notice that if we increase to infinity, it's going to be a very accurate approximation of the area. And we can do a similar thing, however, using rectangle columns instead. So if we have this kind of rectangle column, and let's say the width is delta x. So this is actually called delta, just means change in x. And this is a really common notation when we're talking about this thing. I can have this as 1, as 2, as 3, and so on, as I wish. It's actually sitting on the x-axis just like this, right? So I'm actually just zooming it in for us to be able to clearly see it. And what we can see is that if the rectangle is actually sitting something like this on the x-axis, right, then the y value here, for example, if this actually has the width of delta x, right, and it's actually starting from maybe like a x value called x1 and another x value called x2, so basically delta x is equals to x2 minus x1, because this is like the width at this part right here. And so if we want to evaluate the y value at this position, well, we can just use the function notation, right? So basically this y value here is going to be f of x1, right? Because we are referring to the y value at this position x1. So this rectangle here has the height, right, of f x1. The thing with this rectangle is that we can just kind of make a bunch of these stack in between this area. And so by summing all of these small rectangles up, we can get an approximate area for the area under the graph of this region, like so. If we do something like what we did for the circle, which means the slices like approach infinity, in this case of the area under the graph, we can make these number of columns approach infinity. It's the same idea, just kind of applied to a slightly different context, all right? It's maybe a bit hard to grasp, but for example, if we have these kind of rectangles, like maybe this thing, this thing, this thing, so it just fills the area under the graph. Okay, so the area under the graph, that will equals to, since this has the width of delta x, we can just write delta x times the y value, which is the height of the rectangle, f of x1, and we simply can do this for like many x. We can just plus delta x times f of x2. X2 can be here. We can plus delta x times f of x3, and x3 can be here. If there's like n columns, then we're going to plus this on and on and on until delta x f of x. And it's maybe a little bit complicated, but it's the same idea. We're just kind of chopping this area into small columns and then summing those columns up together. And so we can write the expression as something like this. This is just like the area of the rectangle, something like this, right? This is just the approximation. But if we want to make this the exact area under the curve, then we have to make this number of columns that we are stacking approaches infinity. We just use the limits that we define. So basically we can just kind of sandwich in the limit as n approaches infinity right into the definition of the area that we just written. And that, my friends, is the official definition of integration. In textbook, it's often written as something like this. This is called definite integration or definite integrals. And definite because we're in a specific bound. In this case, we're starting at x equals 2 and we're ending at x equals 4. The way we express this is through this kind of two value right here. So in this case, it's going to be 2 and 4, right? So this one is called the lower bound and this one is called the upper bound. And the way we express integral is we write it something like this, like this kind of curvy symbol, and we have the function that we are evaluating the area under it in the middle, and then we sandwich it between the symbol dx, which if you remember from the definition of derivative, is df by dx, right? And this dx is kind of symbolized that it's a small tiny amount of x, and that is because when you make the number of columns approaches infinity, then the width of each of the columns are going to be approaching 0, right? As this gets a lot, this is going to get even more tiny to fit in even more columns. And so this thing actually approaches 0, and when it approaches 0, it's kind of like the same thing that we write for the derivative. We write limit as h approaches 0 of f of x plus h to minus f of x divided by h, and that h just kind of symbolizes the same thing. And so this is how we write it as a notation. You can think of it as like the function itself times delta x, but just written in this notation right here. And that is what we written in the previous slide. So with this setup in mind, how do we even compute this in the first place? Because in the definition of the derivative, it's much more intuitive on how we're actually going to compute this. So for derivative, we just kind of take this and then minus this and then divide by this, right? But how do we even do that in integral? Like, we have infinitely many sums. Are we actually going to plus all these together? The answer is no, because we actually have a bit of trick. This trick actually originates when you ask the question of what is the integral of a derivative? Well, what I mean is something like this, right? So we know that the derivative df by dx, and we know that for the integral, it's going to be integration from maybe like a boundary a to b df by dx and dx, right? Basically, we just kind of take this thing right here and just sandwich it in between. And what I'm going to do is a bit kind of mathematically wrong, because if you're going to write it as a proof, you have to write more than what I'm going to show you. But basically, dx here, it's the same thing. And so we kind of able to cancel it since it's divided by one another. And what we end up with is integration as a to b of df. And since df means that it's a really small f, right? It's approaching 0. And so by summing them up, you are going to get the original f. Just remember a bit, what I'm writing here is mathematically wrong, but this is essentially the idea of it. If you take the integral of the derivative, what you actually end up with is the original function itself. This just means that integration is the reverse of the derivative, because if we perform this reverse operation, then it's going to end up at the original function that we started with. And that means that these two things are actually reverse of one another. Proof itself is actually kind of a bit more complicated than I can write here in this context, but these two things are reversed. So by knowing the derivative, you can in a way find the integral. And this is actually a very important fact in calculus. This is actually called the fundamental theorem of calculus, and this saying that derivative is the reverse of integration. So with this in mind, we can now compute the basic integration of basic functions. For example, maybe x squared that we worked with in the previous episode or something like that. And so let me introduce you to a more kind of formal way that we're going to be evaluating in the integral, which is what we call indefinite integral. So if you see, we talked about definite integral in the previous slide, and that is where we actually derived the definition of integral. But for the indefinite integral, it's basically like a reverse derivative. And you can see that there's actually no values that indicate the bound of that integral. And this is essentially just kind of a placeholder for you to do the inverse operation of derivative, and you just kind of end up at this expression before evaluating the bound. If you actually evaluate the inverse derivative, you can get something like this as like a function of some kind. I write it as f, large F of x, and then plus c. C is a constant. We had a plus constant because when we take the derivative of a constant, it's actually zero, right? For example, if we take a derivative d by dx of maybe 2, that is 0 because 2 isn't changing at all. So when we evaluate the change, dx is going to be 0. Because of this, when we take the inverse process of it, we have to kind of add the constant back, but we don't really know what constant to add back, so we just kind of leave it as a general c here. With this, you can actually evaluate the definite integral by taking the inverse derivative of like the top and minus the inverse derivative of the bottom. Yeah, so basically this is how you actually evaluate the definite integrals, and there's some proof behind this, but I'm not going to talk about it in this video because I want this video to be only like 20 minutes. And so with this kind of definition in mind, just keep in mind that this is actually related to the fundamental theorem of calculus, and you can actually prove that integral is just kind of like the reverse derivative minus together. We cannot evaluate some basic function. For example, we cannot find what is the definite integral of x to the n. Well, you know that if you take the derivative of this df by dx, then you're going to end up with nx to the n minus 1, right? So if you don't remember this, we actually proved this in the previous episode. To reverse it, you have to divide by n, right? And you have to kind of plus 1 here to actually get back to here. In the same way that we do to reverse the derivative of this, we can write that the indefinite integral and write it as integration of f of x dx. It's going to be plus 1 on top, right? So we can write plus 1 on top, and we have to divide it. But you remember that we can actually write this one as n minus 1 and then just plus 1 again. And so we just divide it by as plus 1 and then plus the constant because we don't know what the original constant actually is. And so we have to plus this as well. Essentially, it's just reversing what we do in the derivative to find the indefinite integral. And so we got that for the function of x to the n. The indefinite integral is going to be x to the n plus 1 minus n plus 1. And with this, we can now evaluate the indefinite integral. For example, the function we are familiar with, x squared. Then if we want to compute the integral from 0 to 3 f of x dx, then what we can do is simply, it's going to be the x to the n plus 1, and in this case it's going to be 2, right? This thing is going to be x, n plus 1 is going to be 3 divided by 3, and this is evaluated at x equals 3, right? Because we have this on top, at minus x to 3 divided by 3 of x evaluated at 0, which is our bottom bound. And we can just compute this. X cubed is going to be x times x times x, and that's going to be 27 divided by 3, and then minus, this is 0, right, divided by 3. And so this actually end up at 9. And that is the value of the definite integral of this expression right here. And so that's the basic way on how we actually compute the integral, but there are actually much more advanced technique in actually computing these integrals. So there are techniques like use substitution, integration by parts, trigonometric substitution, and so much more that you will learn in things like calculus 2. To be fair, one thing that I want to know about the integration is that if you have learned about how to compute a derivative, you might think that integration is similar, right? You can just kind of plug it into some formula and that's you get the result. But the answer is that integration is actually much more harder to evaluate when compared to derivatives, because in derivatives we have different formulas you can work with. For example, you have the product rule, the chain rule. You can actually just kind of manipulate and just eventually get the answer. But integration, there isn't that much kind of technique you can really do. So it's much harder and you have to be much more creative in order to determine this kind of thing. And there's also one sport that actually focuses on evaluating the integral, and that is called integration V. The sport is essentially based on using these techniques to evaluate the integral. I actually been one of the school representative myself in integration V. It's actually a very fun sport, and I think if you like math, you should definitely try if you have the opportunity. Talking about some other application of integrals, one application that is used is to reverse the graph. For example, in this case here, you might see there's a lot of weird symbols, right? But this is actually reference to our first example that we talk about, which is the example about the speed meter, right? If you remember, the graph I used to show you is actually like the distance and time, right? But in this case, we use speed in the y direction instead. And so this graph here is actually the derivative of the original distance graph that I showed you. Since integration is just kind of like the inverse of derivative, we can use integration to reverse the graph. And so with this function, we can integrate this function right here, and that will result in the original graph that we use for the distance. All right, so by integrating this, you can actually get the curve for the distance. And the other application is that you can actually use it to find areas of weird shapes or weird volumes. For example, this is one of the very interesting shapes. It's actually called gatewheel horn, and it's a shape that the surface area here is infinite, but it's actually contained in a finite volume. And you can use the idea of integration, like chopping into small pieces and then summing them up together in a similar way to what we did in the circle, but for other weird shapes, and you can do it with integration. And that's it for this lesson. So this is only a brief overview of integration, and a lot of ideas in integration are a bit kind of complicated. It's not like derivative or limit where math itself isn't really that complicated. It's a bit hard to explain. I would like to apologize you to that. And that's pretty much it for this series on calculus for dumb babies. This is like the final episode for now that I will be making these teaching series, and I might be making some teaching series in the future, but for now I'm going to stop it here, and I'm going to try to move on some other contents, such as like the Minecraft animation content. If you made it this far, congratulations. And if you like my content, don't forget to like, subscribe, and also comments. I want to thank you guys for watching this, and if you watch all the 4 episodes of Calculus for Dumb Babies, I am really grateful for that. Be sure to leave a comment in this video. I hope you have a great day, and see you guys later in other videos. Bye bye!